Next, we're going to cover valence bond theory. Now, I have to warn you at the outset that as we go over the slides for this conceptually, this is probably going to seem extremely abstract and really hard to follow. And that is normal when this first comes up. The good news is I'll show you a couple of representative examples after we cover this section, and the types of questions that you can be asked about valence bond theory on pretty much any general chemistry test basically boil down to just one short chart that I'm going to show you at the very end of this section. But I do want you to understand this stuff conceptually because it is important both now, but especially if you, say, take organic chemistry later. So valence bond theory tries to take what we've talked about in terms of Lewis structures and make it fit a little bit better with the quantum mechanical model of the atom that we now know is true in sort of modern nuclear, well, I shouldn't say nuclear, but atomic physics. And what we're going to do is we're going to basically account specifically for the orbitals that overlap to form bonds in molecules. As with before, we'll start with hydrogen molecules, H2, the simplest possible type of molecule really, since we just have one hydrogen atom bonded to another hydrogen atom, and they each have one electron. So, as you know, the ground state of a hydrogen atom has that one electron in a 1s orbital. And the 1s orbital, of course, is spherical in shape, so you can see the spherical shape of those orbitals on this screen right here. Now, for those electrons to come together and pair together, a couple of things needs to happen. So, in order for them to basically be in proximity with each other, the orbitals need to actually overlap. So, the 1s orbital of one hydrogen needs to overlap with the 1s orbital of the second hydrogen. And not only that, but if we're going to form a bonding pair of electrons, which, as you know by now, is how we form bonds, when electrons are paired, they need to have opposite spins. They're effectively going to end up in the same orbital, and so they can't have the same spin. That's just the Pauli exclusion principle. So you can see our two individual hydrogen atoms with their one electron come together to form a hydrogen molecule where the 1s orbitals directly overlap, and we have two electrons with opposite spins paired together to form a bonding pair of electrons. And if we look at a similar situation with, say, fluorine, as you know, fluorine is also diatomic, so it exists as F2 molecules as a pure element. The unpaired electron in fluorine, which if you draw out the electron configuration for that, you should be able to see why this is true. The unpaired electron exists in one of the 2p orbitals for fluorine. So instead of the 1s orbitals overlapping, like for hydrogen, the overlap between the orbitals of two fluorine atoms needs to happen with the 2p orbitals. And again, this needs to happen in such a way that the orbitals directly overlap and the spins need to be opposite so that they can pair together. One thing to notice in terms of the overlap of the p orbitals is that the p orbitals need to overlap so that the phases are the same. So the pink and blue portions of the p orbital represent the positive and negative phases of the wave function respectively. So they need to overlap basically positive lobe to positive lobe. You can't have pink overlapping blue, for instance. So those come together and overlap with the two orbitals in phase, and they form a bonding pair. Now in both of these examples, we form what's called a sigma bond. This is a lowercase Greek letter sigma, and a sigma bond is basically any bond that forms when we have head-on orbital overlap. In other words, when the orbitals directly overlap with each other to form a bonding pair of electrons. So this is all well and good for these simple molecules. And we get something similar if we have two dissimilar atoms, so let's say hydrogen and chlorine. Chlorine, of course, is a halogen with 7 valence electrons, so it's going to have one half-occupied p orbital in the 3p shell. So a direct orbital overlap can occur between the 1s orbital of a hydrogen atom with its one unpaired electron and the one unpaired electron in a 3p orbital of a chlorine. The 1s orbital has only a positive phase, so it can directly overlap with the positive phase of the 3p orbital. That's why the 1s orbital there is colored pink. And so those orbitals can overlap in phase, and again, they form a bonding pair in the form of a hydrogen chloride molecule with a single hydrogen-chlorine bond. So again, that all is fairly intuitive. Again, we formed a sigma bond in the same way that we saw in the previous slide. It is worth noting, though, that you don't have to have the exact same type of orbital to overlap. They just have to be in phase with each other. So from here, there's some things to consider that haven't really come up when we look at more complicated molecules, say molecules with more than just one single bond. So for this, let's consider methane, CH4. So to invoke the bonding in methane, if we kind of look at the electron configuration for carbon, you might notice a problem right away, which is when we've looked at carbon compounds before, and methane in particular, carbon typically forms 4 bonds. Sometimes those might be double bonds, so it's not necessarily always 4 atoms, but in the case of methane, we have 4 carbon-hydrogen single bonds. Now, this is the ground state electron configuration for carbon, 1s2, 2s2, 2p2. And if you look at this, you might notice that there's only 2 unpaired electrons in carbon. So how are we going to be able to attach 4 hydrogens to our carbon atom? We should only have 2 positions available to do that. And so to explain the bonding in methane, there's a couple of things we need to explain. So one is the fact that we need to have 4 unpaired electrons to have in separate orbitals for the hydrogens to overlap with. So clearly there's going to be some sort of promotion of a 2s electron into a 2p orbital. So this is not the ground state configuration anymore, which is what you write out when you do a basic electron configuration. This, of course, is an excited state electron configuration where we've got 1 electron in a higher energy orbital than it otherwise should be. And we have 4 unpaired electrons now, so you might think, okay, that gives us 4 places for our hydrogen atoms to overlap, so can we explain the bonding in methane just by assuming that carbon starts from an excited state electron configuration? And the answer is that there's actually one other factor to take into consideration, which is probably a little bit less obvious, and that is whether we have the ground state or the excited state configuration of just a single carbon atom, we have different orbital energies between the 2s and the 2p orbitals. That's why you fill the 2s orbital before the 2p orbital, as you know. So we need to account for the fact that not only do we have 4 carbon-hydrogen single bonds, but in fact if you kind of go in and experimentally analyze this, all 4 of those bonds have exactly the same length and the same strength as each other. So there's the exact same amount and type of overlap happening between the carbon orbitals and the hydrogen orbitals, and that wouldn't really make sense if one of those hydrogens was overlapping with the 2s orbital on carbon and the other 3 were overlapping with different 2p orbitals on carbon. So what we need to invoke is the concept of hybrid orbitals. And so what happens is we start with this excited state electron configuration of carbon with a 2s orbital and 3 2p orbitals, each half occupied. And what we're going to do is we're basically going to combine our p orbitals and our s orbitals into 4 new orbitals that are different from the atomic orbitals 2s and 2p. So since these orbitals arise from the combination of an s orbital with 3 p orbitals, we refer to them as sp3 hybrid orbitals. So this isn't something that happens to just an individual atom like you would consider when you're writing out electron configurations for atoms, but it's something that can happen to atoms within a molecule when they're bonding with other atoms in that molecule. And so we have these hybrid orbitals, and the evidence for that is that we need to have all 4 of those orbitals with the electrons in them be exactly the same energy, and that simply can't happen if we have 2s and 2p orbitals separate from each other. And so the carbon atom in methane is said to be hybridized, and specifically to have sp3 hybridization. And again, the sp3 tells you that 1s and 3p orbitals came together to form these hybrid orbitals. If we take a look at kind of what these look like, so you've seen s and p orbitals before. S orbitals, of course, are spherical. P orbitals are those dumbbell shapes. They have different orientations in 3D space. Now, the phase of the 2s orbital is basically all positive, and the p orbitals are half positive, half negative. So when we combine these, what we're going to get is some new orbitals, 4 new orbitals, the tetrahedral sp3 hybrid orbitals, where the positive phase of the orbitals is a little bit larger and the negative phase is smaller. And so we get a shape that kind of looks like a p orbital, but we shrank the negative phase and we grew the positive phase. And so what you see circled here is an sp3 hybrid orbital, and all 4 of them have that same shape. And they're going to arrange themselves in a tetrahedral configuration around our central carbon atom just due to electron-electron repulsion. So this is as predicted by the Vesper model. So once we take into account that we have those 4 hybrid orbitals, sp3 hybrid orbitals, and they each contain 1 electron, now you can see how we can pretty easily take our hydrogen atoms with their 1 electron and overlap them directly with one of these orbitals. Since we have 4 orbitals on carbon and 4 hydrogens with their 1s orbitals to do this, we end up with 4 bonds of the type that you see here. So a direct overlap between the 1s atomic orbitals of hydrogen and the sp3 hybrid orbitals of carbon. And that gives you methane, and it accounts for the fact that all 4 of those bonds are equivalent and that we have a tetrahedral shape for this molecule. Now, it turns out that you don't just have to have sp3 hybrid orbitals. In fact, we can form hybrid orbitals between, say, an s orbital and only 2 of the 3 p orbitals. So this is a situation that happens in many molecules. So the way that this works is, instead of taking all 3 of the p orbitals and hybridizing them with the 2s orbital, in the case of carbon, what we're going to do is we're going to combine 2 of the p orbitals, specifically px and py, not that that is really important, and we're going to hybridize those with the 2s orbital. So we get 3 new orbitals out, and they basically come from combining 1 s orbital with 2 different p orbitals. Now, compared to an sp3 hybrid orbital, the sp2 orbitals are 1/3 s orbital character instead of 1/4. So what that means is that the exclusively positive character of the 2s orbital is going to basically give us a similar shape to an sp3 hybrid orbital, except it's going to be even more lopsided. So the positive lobe is even larger and the negative lobe even smaller in a sp2 orbital than it is in an sp3 orbital. Keep in mind, of course, that when we have 2 of our p orbitals hybridized, that means that we didn't use one of our p orbitals in the hybridization process. So specifically the pz orbital, which is right here, isn't one of these green hybrid orbitals, it's still a regular p orbital. And that's going to affect our molecular geometry and the consequences for some of our bonding. So for this, we can actually consider a carbon-carbon double bond. This is a situation where sp2 hybridization takes place. So I just told you that if we have a carbon atom double bonded to another carbon atom, that we'll have an sp2 hybridization situation. So let's see how that works. Now we're going to form a sigma bond by overlapping one hybrid orbital on one carbon with another hybrid orbital on the other carbon. So for instance, these two orbitals right here. And of course, those directly overlap, giving us a sigma bond, and you can see that sigma bond right here in between those two carbon atoms. Now, let's say we're going to form a second bond. In fact, we are, because we're considering a carbon-carbon double bond. Because of the orientation of these orbitals, so you can see the sp2 orbitals are trigonal planar in arrangement. Once we have a direct orbital overlap between those two, we're not going to be able to do it with any of the remaining hybrid orbitals. They're just too far apart to be able to overlap each other. And even with the unhybridized p orbitals, where the electrons are here in these pink lobes of the two individual carbons, those are still perpendicular to the hybrid orbitals, so we can't directly overlap those either. So while we do have a sigma bond formed between our two carbon atoms from the overlap of one hybrid orbital on one atom with the hybrid orbital on a second atom, our second bond can't be a sigma bond because it's not going to be direct orbital overlap. In fact, it's going to be what's called a pi bond, and it uses the same Greek letter pi that's used for that mathematical circle constant 3.14. It's not related to that constant, it's just referring to the fact that these orbital overlaps generally occur between unhybridized p orbitals, and pi is the equivalent Greek letter to the Latin letter p. So you can see here that, let me go ahead and draw it in, the p orbital on one carbon just kind of expanded out until it merged with the p orbital on the second carbon, and vice versa. So this is where that indirect orbital overlap occurs. The two orbitals aren't meeting head-on, they're kind of merging into each other. And so when we have two bonds between two carbon atoms, or indeed any double bond really, what we're going to have is one sigma bond from the overlap of hybrid orbitals and one pi bond formed from the indirect overlap of unhybridized p orbitals. So that's an sp2 hybridization case. There's one more case to consider, which is sp hybridization. So that's just taking our 2s orbital, in the case of carbon, and hybridizing that with just one of the three p orbitals. So that gives us two new hybrid orbitals, which are sp, because it comes from one s and one p, and that leaves us with two p orbitals, which are, of course, perpendicular to each other, that are not part of the hybridization. So we've got an unhybridized p orbital on the z-axis and another one on the x-axis, and the sp orbitals are perpendicular in 3D space to the other two. Now, sp hybridization probably shows up most commonly when we have triple bonds. So specifically a carbon-carbon triple bond, although other triple bonds would work as well. And again, if you kind of consider the distribution of the electrons between the p orbitals and the hybrid orbitals for each of these individual carbon atoms, you can see we have 4 unpaired electrons. Again, we can form one direct overlap between our sp orbitals, but we need to form 2 more bonds if we're going to have a triple bond. So just like we can form an indirect overlap between a p orbital on each carbon when we form a double bond, we can do that twice with a triple bond. So once with these p orbitals here that are along the same axis, and then a second time with these p orbitals right here that are again on the same axis as each other, but a different axis to the other p orbital. And so what we get is a situation where we have one direct overlap right here, and then 2 indirect overlaps, one here and one here. So a triple bond consists of a sigma bond from that one direct overlap, and then 2 pi bonds. And in general, you can kind of continue this pattern, not that there's really any bonds we're going to talk about beyond triple bonds, but if you're counting up the number of sigma bonds and pi bonds in a molecule, you look at all the bonds, all the single bonds are going to be sigma bonds, and then if you have any double or triple bonds, all of those consist of exactly one sigma bond, and then any remaining bonds are pi bonds. So a double bond is a sigma and a pi, a triple bond is a sigma and two pi bonds. And like I said, all of this is pretty abstract sounding, because in a way it kind of is, but ultimately it kind of boils down to this chart in terms of the types of questions that you can be asked, at least at this level of general chemistry. So hybridization applies to situations where we have somewhere between 2 to 4 charge clouds, and as discussed in previous sections, you know that if we have 2 charge clouds, the charge clouds are going to be in a linear arrangement. If we have 3 of them, they'll be in a trigonal planar arrangement, and if we have 4 of them, they'll be in a tetrahedral arrangement. And those charge clouds are your hybrid orbitals. And so each of these possibilities corresponds to a specific hybridization. If we have 2 charge clouds, we have sp hybridization. If we have 3 charge clouds, we have sp2 hybridization. And if we have 4 charge clouds, we have sp3 hybridization. And the number of charge clouds is always equal to the number of hybrid orbitals, and that can help you remember what hybridization goes along with each. Since, for instance, with an sp hybridization, that's 1s and 1p, so 2 hybrid orbitals. For sp3, for instance, we have 1s and 3p orbitals, so 4 total hybrid orbitals.